So good morning, everybody. I'm Atul Jain. I'm a faculty in the Atmospheric Sciences Department at the University of Illinois. Um, Welcome to this first session of this Congress. So this session is important and timely. The reason being the science community now generally agrees that the Earth's climate is changing, and it's in the response of increasing greenhouse gas concentrations as well as the aerosols. In addition, agreement is also widespread that these changes have a huge and large impact on our hydrological cycle. In particular, the water content in the atmosphere, precipitation patterns, as well as runoff and the stream flows pattern. However, many uncertainties remain in the prediction of climate change, as well as the impacts of these uncertainties on the hydrological cycle, as well as resources. Well, we have three excellent speakers today who are going to deal with or also discuss with some of the issues which are important related to the water resources and the climate change. Our first speaker is Praveen Kumar. Dr. Praveen Kumar. Praveen is a professor in the Department of Civil and Environmental Engineering at the University of Illinois. He also presently serves as the director of the Critical Zone Observatory for Intensively Managed Landscape. Before joining the university, Praveen also worked at the Hydrological Science branch at the Goddard Space Flight Center in Maryland. He has served in many national and international advisory boards, including the founding board member for Consortium of Universities for the Advancement of Hydrological Cycle. He is newly elected fellow of American Geophysical Union, and his title of the talk is Structuring the Blue Revolution for Water Security. Please join me in welcoming Praveen Kumar. Announce that there will be first three talks, and then rest after this 60 minutes talk, there will be half an hour discussion question session.
Thank you, Atul, for a very kind introduction. I was told that I should give a disclaimer. 24 hours ago, I was under general anesthesia, so anything I say stupid, please forgive me. Can I get rid of this? Okay, that's not going to go away. Okay, so I've been thinking about the water issues for a while, and a few years ago, I think about 4 years ago, I was talking to one of the advisors to the then Prime Minister of India. He had an advisory board of 12 people, and one thing that came to mind is that India has been very strong as a policy on food security, and as a result, they have more food than they can consume at this time. I mean, they are sufficient in food. It's a distribution problem, the poverty, not so much lack of food. But water, as you know, is a big problem. And in discussion with him, I said, well, India needs to adopt a water security policy rather than a food security policy. So the food security should be part of water security. And his question was, okay, so what should we do? And so I had fragmented answers, and I don't think I have a coherent answer as yet. But what I do want to do is at least present some ideas in that regard and see if there is a way for us to move forward and if that will help solve some of the problems. So this is a picture, Save Water, which I took when I was in Mumbai, formerly Bombay, and the need to conserve water is being advertised everywhere, right? So let me start by telling you a story. Every landscape has a story, and the story I'm going to tell you is what I have learned a little bit about from the critical zone effort that Atul mentioned. So we presently, somehow I have to be able to get rid of this thing. It just where is it?
I think you can click and drag it.
Oh, I think I should drag it, but the.
When you're in, yeah, now click on the edge of it and drag it.
How about I click this guy? Nope, it's a persistent virus. We'll make it irrelevant, at least for now. Okay, thank you. So our part of the landscape, about 10 to 12,000 years ago, was glaciated, and so the last glaciation period ended about 10 to 12,000 years ago. But this dark area is the extent of glaciation around the globe, and since then we have vegetation growing. So if you look at the glaciated land, so this is this area here in the dark area. So at that time you would have periglaciated area, and then we would have had forested area. So nothing was growing where we are, right? And over a period of time, there were seeds which were carried by wind from this forested area as this glaciers receded, and they took hold, and we had wind-blown soil, which is now called loess in our area. And so with this wind, seeds and wind, there's vegetation that is growing, and so there is plant-soil co-development. So this area was colonized by plants that needed low nitrogen, and then there was arrival of nitrogen-fixing plant, and therefore establishment of fungi and arrival of trees. So all this happened within the last 12,000 years in our area, and then there was a northward migration. So things get established, and then you have migration about 100 to 300 meters per year. That's the rate of migration. So we have basically, because of the glaciation, there was silt, there was outwash, and there was some heterogeneity that developed in this particular part of the land. And there was heterogeneity of soil organic carbon, nitrogen, etc. And as a result, we got very, very productive landscape, right? So, but if you know, this area has moderate to low gravitational energy, and therefore the long residence time. Water stayed in the landscape for long periods of time, so slow transport, and we enjoy moderate solar energy, so the transformations are slower, so there is a high accumulation. So although we have a productive landscape, it is rate limited for intensive agriculture. Okay, so the natural soils are great, but it is rate limited. So for agriculture to happen, we had to basically overcome this rate limitation. And as a result, basically we put in tile drains to remove the water in this upper zone of soil. There were channel extensions, channel straightening, which you can see here, fertilizer use, biotechnology for seeds, and mechanized land development. So as a result of all this, basically what we're doing is we are putting in a lot of extra energy, anthropogenic energy, into the system. So this is a figure that one of my students put in, and basically a lot of these energy come in form of nitrogen, machinery, fuel, you name it, right? And basically we get an input to output ratio of 1:4 in this landscape with respect to this energy. But this energy is about 10% of the net solar energy per year. Right? And this is applied in a very, very short period of time as compared to the annual distribution of the solar energy. So this has essentially resulted in a very productive landscape. But for that to happen, there is a whole suite of institutional networks that have evolved, which is basically going from farms to drainage district to soil water conservation district, regulatory authorities, USGS for measurement, university extensions, local markets, global markets, government, Department of Natural Resources, Army Corps of Engineers, and many others, basically. So all these institutions essentially work together in some ways, or they're supposed to make a lot of the things happen in this particular landscape. And as a result, what we have is basically a lot of economic value coming out of agriculture, but also a lot of problems with hypoxia, right? So despite all the best efforts of these networks, we have both a positive consequence as well as a negative consequence. So if you look at globally, that was just an example of what happens in our landscape. We have a water scarcity problem. So wherever you see the warm colors, there is water scarcity. California should not be blue at this time, but nevertheless, on the other hand, wherever there is blue, there is a lot of available water, there is a lot of water quality problem. So if you look at globally, either you have water scarcity problem or a water quality problem, and each part of this landscape will have its own story as to how it got there, right? And water science is to a large extent place-based science. So we need to look at the uniqueness of the place and its role in specific problems. And we need to somehow come up with ways to resolve this. So we are entering in a new era of sensing, right? So we can pretty much sense all aspects of environment now. And the question is, how do we use this information to guide our decisions? And as an example, I'm just throwing this to illustrate the point. For our critical zone observatory, we got some LiDAR data, and pretty much you can resolve each tree from this information. And not only you can resolve this tree, you can also basically classify the species of these trees and look at the vertical structure of these trees. So my point in this is that we are entering in an era of sensing where we can pretty much identify at very, very high resolution what's going on our landscape. At the same time, with the sensing, there is evolution of cyber infrastructure. And if we look at the role of integrating data and decisions, there generally seem to be a disconnect. So if we look at the data life cycle, we go from needs assessment to data collection to experimental planning, and then we go through looking at data, integration, ontologies, and so forth. We look at analysis, use of this data, and then we basically preserve to some degree what this data is. But if you look at the discovery and decision life cycle, and you go from problem to hypothesis, you look at modeling, discussion, and analysis, and we publish things. There might be community adoption, there might be verification, and then we go into design, assessment, modeling. But a lot of these policy assessment, they are not data-based. They are basically coming out from a disconnected cycle, which should be integrated. And we are getting to a place or a time period in which our cyber infrastructure can allow integration across this entire connected system so that we can make better and informed decisions. So with that as context, I've just talked about water quality issues, but if you look at the facets of water crisis, there are many. They are related to food, they related to sanitation and consumption, related to climate change, pollution, use of water bodies, energy and development, ecosystem services, extremes. So the use context of this water crisis is many, and similar analysis can be done for looking at all aspects of this. So the question arises as to how did we get here? Okay, so one can say that this was a problem that was inevitable because of population increase, growth, and development. You could say that this is a problem created by our own solutions because of infrastructure and waterworks development to support the green revolution. A problem created by lack of social and political will, like the pollution management. It's a problem of collateral damage, like climate change. It's an emergent problem from unexpected drivers. So, for example, energy prices driving biofuel production, which then puts pressure on water demand. And a problem when collaborators became competitors. So energy, food, and water. So the green revolution was brought on because of availability of energy and water, but that is no longer the case, right? They are now competing for the same resources. So the water crisis is essentially a question of availability, use, and management, and also that of access, quality, and scarcity. So given this highly interconnected system where we have natural and human systems, so these are trade routes across the globe, and this picture, which I like very much, illustrates how we live in a planet which is not just natural and human systems are divorced from it, but basically they are interconnected. And our colleague Megan Kumar had published some work in WRR where they were able to show that the food trade essentially has a network, and there is a virtual water transport. So when a food is grown in the US and is transported to Japan, it's like transporting water in there. So whatever we do, I mean, there is a local context as well as there is a global context, and one cannot solve the problem just by looking at only one aspect of the problem. So what are the key challenges? What are the central challenges? So basically we're looking at exceeding the limits, right? The growth far exceeds our knowledge of predicting and managing coupled human and natural systems in terms of consequences, be it climate change, in terms of emergent risk because of increasing interdependencies in there. So we need to look at this in some sort of an integrated way. And what I'm advocating is basically looking at it going from traditional systems approach to a network approach. And when we have a network approach, we really need to look at the networks that connect public policy and investment, laws and regulations, markets and trades, climate, water, energy, food, cyber infrastructure, and others. So the question is, how are these networks connected? And so the factors of interdependencies across these networks related to physical, so real or virtual material flow, related to cyber, information, and knowledge flow. They may be geographic, so local, competitive, and cooperative interactions. And they may be logical, so example, policy and development, which essentially has no flow, but it affects what we do as a consequence. So what we do have is a cascade of emergent risk and failures, right? So water crisis is arising because we don't know how these interdependencies work, and we don't really understand how these things cascade. But this lack of integration, you can see, essentially is between science and society. Are we using all we know to address societal issues? Are we using all the information that is available to us in terms of decisions? Are we developing policies that go with societal priorities? Is there a disconnect between resources and values? And perhaps there is a disconnect between laws and evolving societal norms, because some of these laws and regulations were put in place long time ago, and we're still suffering the consequences of that. And economics and scale are market systems taking advantage of the scale. And is there a disconnect between social and private value? Public use of water versus private use of water. So there is a whole suite of things which seem disconnected, and a lot of us are addressing each of these problems, but not so much working to resolve the interdependencies across sectors and across scale. And as a result, what we have is what has been called planetary scale critical transition. This is in the context of ecosystems, where over a period of time, essentially, the situation gets worse, and you have a threshold behavior where basically to recover from this, you cannot just go back to the previous state, but you have to go back to a very different state before you can recover. So it is this kind of cascade, or what I would call as an emergent risk, because once you fall off the curve here, there is no way to recover, that we really need to understand through these through these interdependencies. So in some ways, this could be characterized as a hyper-complex problem. So the thing is, the cause and effect for water are separated in space and time and across generation. What we do affects generations later. And there are often social barriers for effective solutions. Even though you may know what is the right solution, you may not be able to implement them because of interests of people. There is, of course, emergent risk, because you don't know how the systems connect, and when the systems connect, new risks arise. And these emergent consequences that are at all scales. And we are faced with duality of choices all the time. There is the choice between growth, which is immediate, and intergenerational equity. There's a choice between conservation and progress. There's a choice between local drivers, local response, and global response. So when we're looking at this idea of addressing water crisis and what I would call the blue revolution, we need to develop a framework of integration. So if we are to implement a solution that would be bought by the society, we need to be able to advocate its use or influence across all scales. So the first one is individual. So what would a blue revolution do at the individual scale? So it would provide affordable access to sufficient safe water to lead clean, healthy, and productive life. That's at the individual scale. At the local scale, it provides protection from overuse and hazards of floods and drought, production of economic goods and ecological services, and prevention of environmental degradation. At the national scale, it would provide economic growth and social well-being, including food security. At the regional scale, it would provide equitable negotiated agreements for water rights to avoid international conflicts. And at the global scale, it would provide price stability of products and services. So a concept of water security in the what could be described as a blue revolution would essentially cover a range of scales which would be beneficial to everybody, and that has to be well articulated. So if you learn from the Green Revolution was brought about in many ways because of technological developments for fertilizer production, high yield seeds, development of dam and canal systems, intensive irrigation, pesticides, and herbicides and mechanization. The question is, what is it needed? What is it that we need for water security? And basically, I would argue in a broad terms, it's not just an issue of science and engineering. We need to integrate that with observation, knowledge, and information. We need to integrate that with cyber infrastructure. And we need to get our social and institutional networks to take advantage of all this information in an agile social context. And we can dwell down to a lot of these details, but we really need to structure our water problems and water challenges in a broad framework which is more consistent with what we have at present. So with that, thank you. Questions?
Thank you, Dr. Fu. It was an excellent talk, and we heard about some new approaches to predict the droughts, and we will have enough time for the discussion and questions session of asking questions for Dr. Fu. So our next speaker is Dr. Pradeep Mujumdar. Dr. Mujumdar is a professor in the Department of Civil Engineering and a chairman of the Interdisciplinary Center for Water Research at the Indian Institute of Science in India. He also holds associate faculty positions in the Da Vinci Center of Climate Research in Bangalore. His research focuses on climate change impacts, hydrology, water resources, including detection and attribution of hydrological change. He has served on many national and international advisory boards. He served until recently as the chairman of the Water Resources Management Committee of the International Association for Hydro Environment Engineering and Research. He is recipient of many awards, including Alexander von Humboldt Medal for the European Geosciences Union and a distinguished visiting fellowship of the Royal Academy of Engineering. The title of Dr. Mujumdar's talk is Regional Impacts of Climate Change, Implications for Water Management in India. Please join me in welcoming Dr. Mujumdar.
Thank you very much, Atul, and this is a great privilege for me to present before this audience, and I thank Professor Madhu Khanna for this opportunity. Now, I would be giving a hydrologic perspective to climate change issues, especially on water resources management. And when we talk about water resources or any resources, when you're talking about Indian situation, the first stress that always comes from the population growth, and we are likely to overtake China, and I'm not saying that with any degree of pride, very soon, and we are reaching about 1.3 billion in around 2020s. And as the population grows, the per capita water availability starts coming down, and we are already a water stressed country in that sense. Bulk of our water resources come during the monsoon period. The rainfall occurs during the 4 months of June, July, August and September, and about 70 to 90% of this water is because of the monsoon rainfall. We use about 75% for irrigated agriculture, and we have a long coastline here, and these are our major river basins: Brahmaputra, Ganga, Jamuna, Kaveri, Krishna and so on. These are our major sources of water. So the stresses that come from, in as much as water resources management is concerned, are extremely low efficiencies of water use, particularly in agriculture sector. We have about 35 to 40% of efficiencies, frequent floods, droughts, and what is more important is lack of capacity to forecast and develop responses, contaminated rivers and groundwater, and all other things. Especially, the farmers in India are small farmers in the sense that they hold just about 2 acres, 5 acres of land, and they are poor farmers, and they are given subsidized energy, in many situations free energy, as a result of which They pump the groundwater indiscriminately. The groundwater levels are getting depleted beyond sustainable levels. So these are some of the issues, and the rapid urbanization that is taking place over the last about a decade, with very little space for infrastructure expansion. And we get water, for example, in Bangalore city where I live, we get water from about 100 kilometers with huge pumping. So this has huge energy implications when we are talking about urbanization and so on. So the climate change, in as much as it affects the water management, is an additional stress along with the existing stresses. The three major symptoms of climate change, so to say, namely that the global average temperatures are increasing, the precipitation patterns are changing, and the ocean levels are rising, sea levels are rising. Now these have implications on all aspects of hydrology. For example, the temperature rise, apart from it affecting the circulation patterns and therefore the precipitation patterns, it directly affects the evapotranspirative demands of the crops, and because we are an agrarian society, the water demands dictated essentially by the rise in temperatures. Then the precipitation patterns will dictate the water availability and also the extremes of floods and droughts. And the ocean level rise, sea level rise, what is obvious is that it will cause coastal inundation. But in the coastal areas, we are already pumping the groundwater to a great extent, and therefore there are already gradients existing between the saline water and the fresh water. As the sea levels rise, this gradient increases, and therefore the intrusion, saline water intrusion into the coastal area increases. Much as the global temperatures are rising, the Indian situation is the same. We have similar patterns. This is for the winter, this is for summer, and this is the annual season. So the issues that we need to address in as much as water management is concerned for the country is at the first level, how do the water fluxes respond to the global climate change? And as I said, the river basins are our major sources of water, and therefore at river basin scale, we need to address the changes in the water availability apart from the hydrologic extremes of floods and droughts and all of these issues. Because our farmers depend on the monsoon rainfall, the delays caused in the monsoon onset has a major significance for agriculture. Now, the way we go about doing this impact assessment is this is a classical way we adopt. We use the GCMs because the GCMs work on large scales. There is a scale mismatch. As you move from the left side to the right side on that table, the ability of the GCMs decreases, whereas the importance for hydrologic impact increases. For example, the GCMs are good at larger scales, but what we need really are at a smaller scale. And the variable mismatch, the GCMs are good in the smooth variables such as the pressure variables, temperature variables, etc. But what we really need is the evapotranspiration, runoff, and these issues. And therefore, we adopt downscaling, and from the global scales, for GCM grids, we bring it down to hydrologic scales. We put the extraneous inputs such as the land use and the soil characteristics, all the catchment characteristics, etc. Run the hydrologic models and then provide the future projections. This is what we do at the river basin scales. And on the Indian river basin, as a first cut solution, several river basins were considered for our UNFCCC response. This was done with one model and one scenario by IIT Delhi, and this is how it looks. I won't go into the details of the results, but this is just to give a broad flavor of how the rivers are likely to respond in future, in as much as the runoff is concerned, the water availability is concerned, etc. But we do that with much more rigor and put the GCM grids on a particular for example, this is the Orissa meteorological region, and on that we superimpose the GCM grids and do the downscaling. We adopt the statistical downscaling and look at how the precipitation is likely to evolve in future, both for the summer season as well as the non-summer season. One model, one scenario combination may show a particular type of trend during the monsoon and the non-monsoon season. However, when you do several models and several scenarios, we convert the precipitation into a drought index. This is a standardized precipitation index, and you get an ensemble of predictions, and therefore there is an uncertainty associated with the projections that we are providing. To address these uncertainties, we provide probability distributions into the future, how the probability distributions are likely to evolve. However, what we have done is that we combined the inferences obtained from different models and scenario combinations, and then provided one probability distribution, maybe a weighted probability distribution for this. This has a caveat that all the information that is gathered from several models has been combined into one particular probability distribution. Therefore, we are killing the signals of some of these models. One model may be right and crying out loud that this is not according to what the other models are saying, but we are just combining these. And then to address this particular question, we start addressing the uncertainties with imprecise probabilities and provide bands of probabilities. For example, we look at what is the maximum probability of drought, extreme drought, severe drought, etc. Now, this information will be useful for agricultural planning in that particular region, where we have a bound of probability that we do not exceed a certain probability of drought and so on. What we did with the rainfall, we also do with the stream flows and look at the water availability in this particular basin as an example. Typically, we use the monsoon stream flow as the predictant. That means the projections are provided for the monsoon stream flow. And if you look at the flow duration curves resulting from this, many of the models may suggest that the 70% flow, 70% reliable flow is coming down. And when this happens for the middle level flows, it has implications on irrigation, it has implications on hydropower generation and so on. So on one hand, we are looking at the increase in the irrigation water demands. On the other hand, the supply may be coming down, and these we combine to see whether we can look at operation of the reservoir for hydropower optimization and look at whether we can maintain the same level of performance of the system when this scenario occurs in future. It is not as if we are operating the system in 2070s and so on. The question that we are addressing here is that if such a scenario happens on the current infrastructure, then how are we going to adapt to this situation? And then we look at adaptive responses at the reservoir level to maintain the same level of performance as we have today in the event of the future projections really coming true. And this we do for several model scenario combinations and arrive at one average level of rule curve, reservoir rule curve, which can be operated during, which can be used during the flood periods and so on. As I said, I don't want to go into the details of the results, but this is just a broad idea of what we do in hydrology. Then we look at the irrigation water demands. For our country, irrigation water demands are by far the most most critical demands in water. Municipal and industrial or environmental flows, etc., are negligible compared to the irrigation demands. When we are looking at the irrigation water demands, essentially we look at the evapotranspiration, and the evapotranspiration depends on the rainfall, it depends on the maximum temperature, minimum temperature, radiation, and then the humidity and so on. So we use several climate models, downscale them to the hydrologic scales, the command area scale, and then start converting it into the evapotranspiration. For example, relative humidity and wind speed along with the uncertainty bands. We also look at the maximum and minimum temperatures along with the uncertainty bands. Then use the FAO methodology for looking at the reference evapotranspiration. From the reference evapotranspiration, we start looking at how the crop water levels are likely to, demands are likely to change in future. In most model scenario combinations, we see that the temperatures, relative humidity, etc., are evolving in such a way that for all the crops, the demands are increasing continuously. And the last question that we address is river water quality. Of course, this is a standard figure for any hydrology student. If there is a BOD shock that is provided, this is a classical Stater-Phelps equation. The dissolved oxygen starts dropping down, and then when the shocks are several, the river will never recover. And in our country, there are a large number of rivers which are extremely polluted. So what we do in this situation is given the same datum status as it exists today in terms of the industrial effluents, in terms of the non-point source pollution, etc., if we do not do anything, but just superimpose the climate change issues on this, then how does the river system respond, is the question that we ask. And then we downscale all these variables and look at stream flow, average air temperature, etc. All of these affect the water quality. And once we have the downscaled variables at these locations, we put it into a water quality model and then see how the dissolved oxygen as a first level of water quality indicator is likely to behave in future. We are not doing any physical changes here, just the same given datum status, only the climate change is happening. The stream flows may be coming down, the temperatures may be going up, then how does the water quality respond? The urban flooding is a major issue in our country. It is governed by short duration, high intensity rainfall. So we ask the question, how do short-term intensities of rainfall respond to climate change? Now, when we are using the global climate models or the general circulation models, they are essentially large time scale models, large space scale models. Whereas when we are talking about the urban flooding issues, we need to come down to about 30-minute intensities, 15-minute intensities, etc. These are the times of concentration that happen. And we just look at the historical intensity duration frequency relationship. It gives an indication that for the same duration, the intensities are in fact increasing. Just looking at the past, the intensities are in fact increasing. These intensities are typically the short duration high intensities which cause the urban flooding. Then we do a rigorous analysis by looking at the CMIP5 model combinations and bringing down in space as well as in time, use a scale invariance theory of the hydrology, and then see how the short duration high intensity rainfalls are increasing. At durations such as the ones that cause urban flooding, there is a significant increase. As the duration increases, obviously there is uncertainty is also less, as well as there is not too much of change. Now, we have done this also for other issues related to hydrology and water resources. For example, we asked the question of detection and attribution of global change. Yes, we see a change in the hydrology at a particular location. Can we attribute really to the climate change is the question that we ask. So these are the major science issues that we need to address now. One is that because of several reasons, not only just the climate change, the stationarity in hydrology is dead. So we need to look at the future as a non-stationary future, and then is there any way of addressing the future in using the non-stationary theory and so on. But what is more important is, can we quantify hydrologic feedbacks to the climate system, both to the climate as well as the reverse feedback into this, and quantify the uncertainties and reduce the uncertainties. These are some of the science issues that we would be interested in. But in the water management context, we keep talking about adaptive policies. We keep saying that the irrigation efficiencies have to be increased and so on. But the question that remains is, because of the large uncertainty associated with these projections, to what extent we need to allow for climate change. For example, urban infrastructure, if you are looking at, can we say that you increase the capacity by 20%, 30% to address climate change issues and so on. So these are some of the issues, and especially in the developing world, the problem is that the issue of climate change has added to the confusion and the perplexity of the policymakers, and we as scientific community need to address this particular question responsibly and see whether we can in fact reduce the uncertainties associated with the climate change projections and provide for the policymakers implementable adaptive responses. That's all that I wanted to say. Thank you for your attention.
So now the floor is open for the questions for our three speakers. Please, Praveen.
I won't be shy. It's very clear from the presentations this morning that this is an extraordinarily complex issue that is biological, biophysical, atmospheric, and economic. And from Professor Fu, from your presentation, prediction is really important. So we know that that's very important. But one of the things I was curious about that was missing in your talk, and you kind of touched on it when you showed the picture of the rancher looking at his failed livestock, was I was looking for a graph of avoided economic loss on the y-axis and prediction time on the x-axis, because, and every industry is going to have a different graph like that. And so wouldn't this guide what your success is? Very clearly, if you could predict this year what next year is, that would be a great success. But you mentioned that livestock could be moved. How much of a lead time does that industry need to know to move livestock? And what's that prediction time important for various different industries?
That's a very good question. I think the lead time required for mitigate drought impact for different industry, that's beyond my area of expertise. But for water resource planning and also for this particular case, mitigate drought impact on cattle, few months would be very helpful. In Texas, for example, the river authority in Central Texas, Lower Colorado River Authority, they have a drought protocol. And usually in January, they will inform all the water user, whether they would get their allocated water. And especially for rice farmer in Texas, this is crucial. So in that case, 6 months lead time is very important, because once they issue the water allocation, and it's very hard to call back, and it's a legal issue. Although after 2011 drought, we had a lot of workshop together, and they implement another step of drought protocol basically in April. And if they found the drought is coming, and they have a right to revise the water allocation. And this policy is actually more in line with our capability for predicting drought, because in many cases, we would not know for the uncertainty of our drought prediction in January is often too large, and in part because part of the drought cause is perhaps not predictable with a 3-month lead time. So that's a long answer to your short question.
Okay, this is a question to Professor Mujumdar. So you presented, I know this session is about climate change impacts on water resources, and what I heard from you, from the Indian experience, when it comes to climate change impacts, the key word that I kept hearing from you was uncertainty. But one thing that you said at the beginning of your talk about the population increase in India, the key word there is certainty, that population rise is certain. So what is your message to the rest of the world, from the Indian experience? Should we focus our efforts when it comes to water resources and water crisis? Should we focus on worrying about uncertainties with respect to climate change predictions, or worry about the certainties about the human population increase and the implications of that for the water crisis? Which is more important?
Thank you very much, Professor Shivapalan, for that question. I would like to straight away say that we should be concerned about both, especially in the context of countries like India and China. Population is a major stress, and that in fact is a certainty. But at the same time, when the stresses that already exist because of the increase in the population and the decrease in per capita water availability, these stresses perhaps may get emphasized when we superimpose the climate change issues on this. And therefore, the uncertainties that the climate change brings along must also be addressed simultaneously, is my short answer. I would like to also state here that when we say uncertainties, both types of uncertainties, such as the epistemic uncertainty as well as the aleatory type of uncertainty, the latter being uncertainty because of our lack of knowledge or imprecision, these perhaps should also be considered when we are looking at the societal systems to be brought into our arena of water management and so on. Thank you.
I have a question for Professor Kumar. Praveen, firstly, thanks very much for a fascinating talk on the complexities of water security. At the end, you were looking at the different scales at which we may look at this, from local right through to international global scales. But it seems to me when you look at a lot of river basins, many, if not all, are transboundary by definition, so that the demands of the upstream countries may be very different to the downstream countries in terms of their water security needs. I was wondering how what views you may have on how a network analysis may perhaps help that, that difficulty of actually being able to look at those problems across different national boundaries and what may be done to solve those.
Yeah, thanks, Jim. That's a really good question, and I think it is the network analysis that is needed to basically put everything on the table. I mean, I don't think in an international context, self-interest of one country is independent of the self-interest of another country. Largely, they may think so, but I don't think that is the case. So putting it in a network context as to how, in this case, maybe the upstream, downstream provides a context for putting down the network of water allocation and trade and food, water, climate that you may have. So those should be looked at. I don't know if Professor Kai is here, but he has done some work related to that in the Nile River Basin, looking across these kind of network analysis. And I think that's the kind of thing that is really needed to avoid the conflicts in there.
Rong, your hybrid approach looks terrific for the Southern Great Plains. I wonder if you could comment on how likely it would be for that to be profitably adapted to, first, let's say, the southeastern United States as an example. Your colleagues at Georgia Tech might be interested in that. And perhaps, at least as importantly, to, say, the Southeast Asian monsoon, where the GCMs are not known for being terribly accurate.
Thank you very much for this question. And we're actually exploring about that. From a scientific point of view, this approach could potentially working for most of the interior continent, where land surface feedback played a very important role. For Southeast, it may not work as well because Southeast is more influenced by these synoptical frontal system. And those systems tend to erase the soil moisture memory, we call, or persistence. And it potentially, I had an exchange with Alan Betts. He thinks this method could even work for Canadian area and probably other area in middle of the, like subtropical, semi-arid area, and interior of the continent.
This is, I guess, for all three of you. I question the continuum between predictability and plausibility and consequence. Because a lot of times when you put a policy question on the construct of predictability, there's argumentation of whether or not you can predict versus shifting to the consequence and plausibility of that consequence. And so where's the continuum? Because I'm just building off Praveen's presentation. If you have this hyper dependence and thresholds, there's a plausible argument that you don't have predictability. And so you should be looking at multiple futures and plausibility and consequence. Just where's the dividing line there?
Yeah, Patrick, can I go first? So that is a really good point, and I think it boils down to some extent between empirical and dynamical. So the predictability question we tend to ask generally from an empirical perspective, but the plausibility question is more from a dynamical perspective as things change, what are the new emergent phenomena that may arise, and even though the probability of that may be really low, if it does happen, its consequences may be grave. And so the tools for exploring that continuum, I don't think are there yet. To what extent we can use the ideas of complexity theory to address them and get there is still emerging. But that is the real question. And I think we do not generally address the plausibility question as much as the predictability question. So we get masked in this issue of uncertainty, which is basically a predictability question, but we do not look at the plausible even with, I mean, if it can happen, it may have some serious consequences. So I think that's a really important problem.
Yeah, I would like to make a very limited point on that. That the predictability, especially in the climate change context, is very poor, is well accepted, and especially in the monsoon regions where most of the models fail. But when we come to the water management issues in the context of most developing countries, and particularly so for India, where there are large number of things that need to be set right irrespective of any other points. And there we use whatever capability of predictability we have to as an excuse to set right the things that are already going bad. I am sorry I cannot elaborately answer this because I missed your question. Yeah.
I think that's a great question. My limited experience suggests that it's very important for dialogue between scientists and different disciplines, scientists, the policy, and for example, water resource management. Because this is also related to Evan's question earlier. Ideally, the longer, the greater predictability you can show, or the longer lead time you can provide, the better, the more effective it mitigates impact. But in some case, the system, for example, the drought or flood, may be intrinsically unpredictable for certain, for long lead time. And really the most effective policy is perhaps, or the mitigation, approach probably should be based on, to what extent this is predictable. Beyond that, we might need to use a different approach, a scenario approach. And that's ideal way of working like a climate scientist, the scientists working with policymakers to provide the most effective policy. We seem to be, my own observation is there's a lot of model prediction out there for user, stakeholder to use, but we don't really look deeper to understand, are these model results physically reasonable? Do we really understand limitation of the predictability? And I think you have for gain the trust of from policymaker and stakeholder, especially very high stake decision. As a scientist, we really need to earn that trust. We need to show we did our homework to the best of our ability, and this is what we can do. I think that will provide more, that's the basis for more sound policy and a more sound, probably better balance between predictability and also the
I just want to add quickly to what I said before, which is basically when we look at this network of systems, we need to recognize that there are often latent or weak dependencies that get accentuated under stress and changing conditions, which may not have manifested before, but which will manifest under new situations. And I think that leads to this question of plausibility. And discerning those are not easy unless we have a very careful analysis of the dynamical nature of these dependencies. So characterizing the dependencies is really crucial to asking the question of plausibility rather than predictability.
Questions? So let me ask then the last question. We heard from Professor Fu, as well as from Dr. Mujumdar, about uncertainties in the projections of climate, change, particularly for the droughts. And then you suggest that there could be some other approaches for the local scale, for example, in the US. So I think this question goes for all three of you. So would you suggest some new approaches to actually make some projections or to study the droughts, at least for countries like India, because I've seen that a lot of uncertainties exist. Under giving these uncertainties, what would you suggest? I mean, other approach, we could use some kind of hybrid approach, maybe the appropriate one. At this time, at least, when we have such a large uncertainties in the projections, I mean, which cannot be used to make any policy decision.
Yeah, in fact, this is one of the questions that has been bothering us because the band of uncertainty is so large that we shy away from giving this to any meaningful implementation. So one of the questions that we were addressing is you simply look at the time series of, let's say, historical flows or historical rainfall, and then can we use the non-stationary time series methods to just project to near future, let's say 2 decades, not really to 5 decades, 6 decades, etc. And then see whether this time series projection in fact falls within the uncertainty range, and then use these along with the other ensemble and then provide something. But these are all really nascent thoughts, and we need to address further. Maybe I'll talk later perhaps.
Another aspect, I think, which we don't consider is that we, as physical scientists, always talk about uncertainty. We are not looking at it from how to make decisions under uncertainty and how to adapt. And I think that is what I was alluding to when we were looking at the network of institutions. So the question is, even when there is uncertainty, and we have to live with that until our ability to predict improves, how do we really use that information in an adaptive and an agile way? And how can we connect these institutions or institutional networks? And can the flow of information through these institutional networks be such that effective decisions can be made? So I don't think we have done enough about that.
Yeah. I think our tolerance of uncertainty depend on the risk, and also depend on really different industry probably has a different requirement or tolerance of uncertainty. From climate scientists' view, the point of view, I think it's really important for us to learn from economists, the engineers, social scientists, what are the most important climate variable, what kind of uncertainty matter the most for society decision. Then we can focus on those uncertainty, because some uncertainty may not be that crucial and may turn out to be very expensive to reduce them. But other uncertainty, the stake is so high, and it may deserve more resource and more attention. That's an area we really hope to learn from engineering and social science.
Some other questions? If not, then we should thank our three speakers today for this.